Alright, we're getting ready to start some more with the fundamental theorem of calculus, and we're also going to be talking about some other theorems used with integrals. This first problem, what we're going to do is we're going to find the area of region bounded by the graphs. And so what we're going to need to do is actually figure out what this looks like. This graph is actually 3 the square root of x minus x to the 3/2, or we could say it's 3x to the 1/2 minus x to the 3/2. I'm going to know if I plug in 0, I get 0. And the other value that's going to give me 0 is going to be 3. I don't really care what's going on in between there. I just know that it is going to cross the x-axis at 0 and 3, so I can go ahead and use those as my bounds. So I'm going from 0 to 3 of this 3x to the 1/2 minus x to the 3/2 dx. So what I'm going to do is integrate each one of these. So I have 3x to the 3/2 over 3/2 minus x to the 5/2 over 5/2. And I'll be going from 0 to 3. This ends up being 3 times 2/3, which would be 2x to the 3/2 minus 2/5 x to the 5/2. Well, what I'm really worried about is what I get when I plug in 3. And when I plug in 3, I end up getting 2, it'd be 3 square root of 3. Or I could say it's the square root of 27, which is the same thing. Maybe I'll go ahead and write that way because that's probably how most of you are doing it. So it'd be the square root of 27 minus 2/5, and then when I plug in 3, I have 3 to the 5th power. 3 to the 5th power is 343, so I have the square root of 343. When I simplify all these things, I'd have 2 times 3 square root of 3 minus 2 times 9 square root of 3 all over 5 here. That would give me 30 that would give me, I need to come up here for more space, 6 square root of 3 minus 18 over 5, and I have a square root of 3. I could make a common denominator and make it 30 square root of 3 over 5 minus 18 square root of 3 over 5, and I'd get 12 square root of 3 over 5. Now it's a lot of work. You could have just made it into a decimal as well. I'm going to begin to talk about this and then use this in the next example. It is the mean value theorem for integrals. I'm going to try to draw a picture for you of what mean value theorem is really saying. And what it is saying is that you have some curve, and it's going from A to B. And it's saying the area underneath this curve can be equal to some value of C. Okay, so if I come up here, some value of C, maybe I'll do that in red. And I draw a line across and then down this other area, so I'm going to shade that in red. So the area in black would be equal to the area in red at some point for C. This C is the height of the rectangle, this F of C is the height of the rectangle, and then this is the base of the rectangle. So what it's saying is that the area under the curve is equal to some rectangle that we can create between those 2 points A and B. This example, which I'll start in the next video, is asking you to figure out what is that C value, which will make the integral and the area underneath the curve equal.